Today we're going to look at molecular polarity in covalent compounds, and before we really start with the notes, I want to discuss a little bit about the difference between ionic compounds and covalent compounds to kind of lay this groundwork of polarity. So in ionic compounds we have atoms that give electrons and atoms that take electrons, and what we end up seeing is a complete separation of charge as positive and negative. And so every single ionic compound is truly as polar as it can get because we have a negative and a positive ion. However, in covalent compounds, we have kind of this intermediate sharing going on, and so we don't really have a clear positive and negative side. But what we do have is electronegativity of each atom. And if you remember our discussion of electronegativity back when we discussed periodic trends, we defined electronegativity as the pulling power between atoms, specifically affecting the electrons of a neighboring atom. So the pulling power of an atom on its neighbor's electrons is the electronegativity. As a result, when we're having shared bonds, these electrons are going to be pulled more toward one atom over another, causing what we call a polar bond. And in a polar bond, we have a separation of charge. So our electronegativity differences will create separation of charge. If we take kind of a look at the separation of charge, these are called bond dipoles because if you think about it, we'll have kind of like two poles in a magnet, and that's what's going to happen between our atoms. So reviewing the trend of electronegativity, remember our most electronegative atom is fluorine and our trend goes up towards it. So we will increase up towards the right. You can see that pattern happening with the numbers, excluding our noble gases. So when we are talking about bonds and their separation of charge, we are going to be looking for which atom will have kind of a stronger tug-of-war strength. So I'm going to do a molecule here. Let's do carbon with 4 hydrogens bonded to it. And we're going to assess this for its bond dipoles. So we have carbon and hydrogen, 4 different bonds. Each shared pair is going to represent a different bond. I'm going to focus on this one, but they're all going to be the same. So if I look at hydrogen and carbon, I've got hydrogen 2.1 electronegativity and carbon 2.5 electronegativity. The difference between these is only 0.4 if you kind of compare the two numbers. And so that number actually is kind of significant here because it's telling us that the difference between carbon and hydrogen really is not that much in their pulling power. The number that the scientific community has come up with as kind of that significant number is greater than 0.4 in the difference. Anything less than 0.4 is basically equally sharing. So we would say that this is a nonpolar bond because it doesn't have a great enough difference between the two in their pulling. But if I switch out my carbon for a fluorine, let's say, now my bond changes to a much greater difference, 4 and 2.1. That's almost 2 whole electronegativity values different from one another. That is an extreme pull towards the fluorine. And so what we'll see happen is these shared electrons are going to pull up towards fluorine and not so much towards hydrogen. And we're going to see that we have more electrons, which means more negative charge towards fluorine and more positive charge towards hydrogen because it doesn't have electrons. And that way we have a separation of charge or a bond dipole. Dipole, 2 poles, like a magnet. And we will show a bond dipole with an arrow pointing towards the more electronegative side. So wherever the arrow is pointing, that's going to be our more negative side, and the tail of the arrow will be our positive side. And sometimes people will put a little line through the tail to show that this is positive, kind of just a visual that this is the positive side of our bond. Okay, so a bond dipole is separation. Anytime we see dipole, that's separation. The two poles, kind of like a magnet of charge between bonded atoms. For it to be a bond dipole, it must be more than 0.4 electronegativity difference. And we draw a bond dipole with an arrow toward the more electronegative atom. And that's going to be more negative side. The more positive side is where we have less electrons. So our bond dipole is separation between bonded atoms. Our molecular dipole is kind of the summation of all of the bond dipoles within a molecule. And we really want to assess whether these bond dipoles will balance each other out or if they're imbalanced. And that can be caused by a couple of factors, both the shape and, of course, the bond dipoles within the molecule. So if our bond dipole is a separation between bonded atoms, our molecular dipole is the separation of charge in the entire 3D molecule. If we have an imbalance throughout our molecule, we would say that this is a polar molecule. So polar is going to be a molecule with imbalanced bond dipoles. And nonpolar molecule has balanced molecule dipoles. Or it might not even have dipoles at all. It might just have equal sharing, kind of like the carbon and hydrogen example we did. That would have been no bond dipoles at all because they are all less than 0.4. So it could either be balanced or equal sharing. If we finish off the molecular dipole analysis of our fluorine and hydrogen example, we would have bond dipoles, 4 in total because of our 4 bonds. And although these bond dipoles are very strong towards the fluorine, notice how they balance each other out. We have kind of these left and right and up and down balancing each other out. Or if we consider the shape in 3 dimensions, it's tetrahedral, and we have the 3 legs kind of pulling up, and then we have the top one pulling down. So we've kind of got this balance throughout, up and down equaling and side to side equaling out, making it a nonpolar molecule, even though it does have bond dipoles, really strong ones at that, in the molecule. The overall summation of the molecule does not have a separation of charge. So we would consider this to be a nonpolar molecule. Let's look at the examples, and just like we did here, we need to consider the shape and the individual dipoles to determine the polarity of the compound. Some different shapes that tend to be kind of lend themselves toward imbalance or balance. Let's just list some. So ones that tend to be imbalanced because of their symmetry are trigonal pyramid and bent and linear. So these tend to be an imbalance for their shape. And trigonoplanar is kind of like those 3 little tripod legs. They tend to separate up and down. They don't have that top part of the tetrahedral pulling it back down. They just have it pulling up. So that tends to be the case, causing imbalance. Bent and linear. Ones that tend to be balanced, we just saw tetrahedral, and the other one is trigonal planar. But of course, we need to consider the bond dipoles because maybe perhaps, for example, linear. It might be the same atom, or maybe it's not strong enough, like our diatomic elements. If we had chlorine, those two have exactly the same electronegativity. So even though it's linear, it is balanced, equally sharing, and would be considered nonpolar. So let's analyze each of these compounds here for their shape and bond dipoles, starting with our nitrogen and hydrogen compound. So we've got 3 bonds. I'm going to draw arrows toward my more electronegative element. Check your chart. You'll see that nitrogen is stronger. And this shape is trigonal pyramid, which is in our list for imbalanced. And it looks like this is, you can see imbalance pulling more towards the top. If you draw this like a pyramid, you'll see it's all pouring upward, and we will have more of a negative charge here and a positive charge here, causing a molecular dipole. So we would say this is polar. Carbon dioxide, if you look at your table, we've got carbon and oxygen with a difference pointing towards oxygen. This shape is linear, which tends itself toward imbalance. However, do you see how this bond is the exact same as this bond? So it's balanced in opposite directions, and we would say that this is a nonpolar compound. And our last one, hydrogen and sulfur, we've got 2.1 and 2.5. That is a 0.4 difference. So these do not have bond dipoles. It's equally sharing, even though its shape is bent, which lends itself typically to imbalance. Because there are no bond dipoles, it's sharing equally, making it a nonpolar compound.